Very good morning. Today I will cover the following topics in my lecture, that is the solution of the time independent Schrodinger wave equation, and to solve this equation, what is the use of the boundary condition, what are the boundary condition, why to use the boundary condition, and everything related to that. And last but not the least, the concept of normalization. And I think these 3 points will clearly explain you and how to solve this equation, how to solve this time independent equation. Okay, and after solving this equation, we will get the solution of what is psi and what is E, that means the energy of the particle in quantum. Okay, so before going that, it's time for recapitulation of what we have done previously. Now, previously, we have already shared an idea about how to solve, how to derive the equation of time dependent and time independent Schrodinger wave equation. What is wave equation? What are the parameters? What are the assumptions we have taken? And what are the constants? What are the related equations? Everything we have already covered in the previous lecture. Right, and in the previous lecture we have clearly shown that the step-by-step derivation of from where we started and what we are getting, that is totally the independent of time. It is only the function of x, right? And what was the final expression of this equation? That was minus h squared by 2m del 2 psi by del x2 plus v of x psi equal to e psi. Okay, and what are the parameters? V of x is nothing but the potential, E is the of energy, and m is the mass, and it's a function of x obviously because it's a time independent equation, and psi is nothing but a wave function. Okay, so we have already done in detail of each and individual parameters and their expansion, but today I will cover that how to solve this equation. We have derived this equation, but we don't know the solution. Okay, and from this solution we will enter the concept of normalization, we will enter the concept of the density of states. Okay, and from that we will totally take the entry into the solid state, solid structure, semiconductor, energy band. That notes I have already shared with you, but I will come into the detail portion, and this is all the semiconductor part, and after completion of that we will enter the nanoelectronics portion, the nanomaterial and everything related to nanoelectronics. But this is the basic part of your syllabus. Okay, and it's totally covering the module 1, right? Okay, so now how to solve this Schrodinger wave equation? So for this I will introduce a very innovative concept that notes will be shared with you, a very innovative concept that is known as infinite square potential well, right? Because in our expression, I will write the expression, but just I am now explaining it verbally. In our expression there was a term that is potential, right? That is V of x. So we will use this term V of x to solve this Schrodinger wave equation, right? Okay, so I am writing over here that which concept I will use. That concept is known as infinite square potential well, right? Okay, and you all know this well, right? It's a bounded region. And why we are taking this bounded region? Because it will be very easier to apply the boundary condition in order to get the solution. So that's why we are starting our lecture by considering a potential well, right? So what is well? Suppose this is your bounded region, right? So here it is 0, starting point 0, and the ending point is a, right? So this is all the bounded portion. This is x equal to 0 to a. So this is the bounded portion. Okay, and this concept shows that how potential is incorporated in the Schrodinger wave equation, and from this the realistic wave function we will get the solution of the Schrodinger wave equation. So that's why we are using this concept. Okay, so very clear definition is already there in your PDF note. Please go through this for better clarification. I am just here to explain each and every term that I have already written in my notes. See, this infinite square well, or in a good way you can say that in your syllabus it is already mentioned, that's the particle in a box, right? The particle in a box, particle means a particle, okay, a quantum particle. So in box means a bounded region, so that's why in a box. So what is the nature? What is the nature means is a wavy nature, and this is the related to wave function. So wave function is related to Schrodinger wave equation, and we are here to solve this equation, nothing else. So all are related to each other, right? So here I am writing off this infinite square well, or you can say it the particle in a box, right? It's a particle in a box. This is a box concept, and this is used because we are considering the potential is infinite in this well square, in this square well, right? And it looks like, if I draw as below, and how it will be seen, just watch and see that how it looks like that. Okay, so if we are considering that potential is infinite in this well, in this inside the well, so what will be the expression of your potential? We know that what parameter the potential is, that is v of x, right, in your equation. So v of x equal to 0, where it is 0, 0 less than equal to x less than equal to a, and it's infinite where it is infinite otherwise. So this is your mathematical expression of using the parameter potential to solve this equation, right? Okay, and this potential, I am again clearly explaining that this potential is 0 in between 0 and a, and is infinite outside of this region, because just like that, you're beyond 0 and beyond a, its value is infinite, but in between 0 and a it becomes 0. Because why it is become 0? There is no potential. Potential means no potential energy, because it's a, there is a acceleration. There is this particle will strike some other particle, and this will strike other one. So there is no potential energy in between this boundary, because it's in between 0 and a, but it's infinite in the beyond of 0 and a. So that's why we are taking this expression, and using this concept of Vx, I am again saying we will try to solve this equation, right? Okay, so now I am writing the our main equation, the whose solution we are going to solve. Our equation is the time independent equation, that is minus 8 cut squared by 2m del 2 psi by del x2, and v of x psi equal to e of psi. We all know that what is psi and what is e and everything, so there is no need to explain it once again. So now this is our equation, and what happens outside of the well and what happens inside of the well, which portion we will take for consideration, which portion we will take for solution, right? Okay, so now I will explain each and every condition, that is outside as well as your inside. Okay, so please see that outside of the well means, what does it mean? Outside of the well means this portion, right? This portion. So how can we explain? This is x less than 0, and here it is x greater than a. Obviously, because it is a beginning portion and it is the ending portion. So x less than 0, this region, and x greater than a, this region is the outside of the well. Okay, so if we put v of x equals to infinity over here, then what value of the wave function we will get? What value of the wave function we will get? Yes, obviously it will be 0. So if we put v of x equal to infinity, because we are considering the outside of the region, then we will obviously get psi of x equal to 0. So if psi of x equal to 0, there is no need to proceed for getting the solution of this equation because it is 0. So there is no other way to get the solution. So we will not choose this one, right? Okay. So what is the another way? That is the inside of the well, inside of the region. Okay. And how we can define the inside region of the well? Yes, it is the bounded region in between 0 and a. So if we put that, just a minute, inside the region, that is 0 to a, then what happened? We must say that 0. So what will be the modified equation? That is h squared by 2m del 2 psi by del x2. The put vx of 0 over here, and that is equal to e of psi. Okay, so this is the time independent Schrodinger equation that is going to solve. And now my question is how to solve it. Okay, so please see once again that using the concept of this potential, we have reduced the expression. Okay, and now it is easier because it is simple second order differential equation. We all know the how to solve, how the general equation of the ODE, first order, second order, and so on. Simply we'll use that concept to solve this equation. So now it is nothing but the mathematics, but yes, we will obviously use some concept, use some assumption, use some constant to expand our derivation as according to the condition. Okay, so now this is the time independent equation that is going to solve. Okay, so next portion is how to solve it. Okay, so this is our mother equation. This is our mother equation, and just I said a few minutes ago that what is the solution of the second order differential equation, because this is your mathematics of your previous semester. Just please recall that concept and apply that concept, that how to solve it. I am here to denote that portion which will be needed for the solution part. Okay, so everyone should know that what is the general solution of the differential equation of the second order, because this is a second order equation del 2 psi, this is the power of 2. Okay, so what is the solution? Here is a blank page, so I must write over here. What is the general solution? This is del 2 psi by del x2 equal to minus k square psi. Yes, so this is the part that we will use, and this is a solution. This is a solution part. And what is k square? K square is nothing but the constant, right? And but we also know in our previous lecture that k is nothing but the wave vector, because I have already explained at the time of derivation of your time independent Schrodinger wave equation, and there we obtain some value in terms of energy, in terms of mass, in terms of h cut parameter, and that was k equal to root over of 2me. If we solve this, 2me divided by h cut. Okay, so k is the value of that, otherwise k square is a constant. Now these equation we should recognize. This equation, what is the equation? That is del 2 psi by del x2 equal to minus k square psi. So this is our equation. Okay, because and this is nothing but the equation of simple harmonic oscillation. You all know in your mathematics, in your derivation, second order differential equation part. Okay, so this is nothing but the equation of the simple harmonic oscillation. Okay, so here we are considering the one dimensional time independent equation. So psi must be the function of x, not time, right? Okay, so this is the ordinary differential equation, simply written as ODE. You all know this term, ODE. Okay, and the scenario is, and if we go to the solution part, you all know that psi of x equal to a sine kx plus b cos kx. This expression is well known to you. and this is the general solution, right? So where these A and these B are totally constant, and these are unknown value, but we should define this value. What is the value of A and B, right? Okay, so if we draw this portion, what will be the it will look like? Is nothing but a sine function and a cosine function. So what is your sine function? Just like this. And what is your cosine function? There is a phase shift. Yes. So this one. This is your cosine part and this is your sine part. It looks like that. So it's nothing but a naturally wave function. Okay. But we don't know what is the value of A, what is the value of B, and what is the value of K. So all these are going to be solved. But we must say that we know K in terms of EM that I have already defined previously, this one, and for time independent wave equation. So the number of unknowns we are getting high because A, B, K, all the parameters are unknown to us. Then how to solve it? Yes, we will use the concept of boundary condition. This is a new concept you are hearing, either it is whether it is first time, or I think that in your EM theory portion there is a boundary condition. Hopefully it will be covered shortly, and there you will also get some knowledge about the boundary condition, how to apply the boundary condition. And it is a very easy concept, because if we know the region that is a bounded region, because we have a space, right? But we are considering is a bounded portion. We are not considering the overall portion. We are selecting some portion, and that bounded region there is some limit. Here it is because in between 0 and A, so we are considering a region in a bounded portion, bounded in between 0 and A. So that's why we are applying the knowledge of boundary condition to get the solution immediately, right? So now here is a time that how to solve this boundary condition and how to apply this boundary condition to form the solution. Okay, please see that we have a wave function, right? We have a wave function. What is a wave function? That is nothing but psi of x, right? And now this wave function, we have already known that it has a non-zero value in between 0 and A. Clear? It has a non-zero value in between 0 and A, and it is 0 at the outside of the region. Clear? Because we have already derived that portion at 0 and at A. So from the previous part, it is clearly known that this has the non-zero value in between, I am writing over here, in between 0 and A, and it's a value of 0 at the outside of the region, because we have already proved this, right? Because just know the previous part, v of x equal to 0 means psi of x equal to 0 at the outside portion, but in the inside portion it is non-zero value. Okay, so again I am showing this drawing. If it's a bounded region 0 and A, so this is the region, this portion, and this portion, here the value is 0, here the value is 0, but in between this the value is non-zero. It is already cleared in a previous part. We have already proved this one. Okay, so we know a very couple of things from the previous section, but general form of the wave function, this is our key interest, right? And just from the concept of the Hamiltonian operator and the momentum operator that I have already shared in the previous classes PDF lecture, you all know that what is the Hamiltonian operator and what is a momentum operator, because you have already solved the assignment on that. Hamiltonian, I am again saying that is nothing but the summation of energy, summation of potential energy and kinetic energy, means the total energy. It's known as a Hamiltonian operator, right? So from that concept, in my previous lecture, PDF, I have already mentioned, and you all know this, that most important point, that is psi is nothing but the continuous in nature. Yes, this is a continuous in nature. Okay, this is nothing but a wave function itself, but it should be continuous in nature. Okay, and if we have a wave function just like this, where it is a cut or it is discontinuous in nature, but we will not accept this kind of nature, because in this region the momentum becomes, or any parameter becomes, a strange value. Okay, because we all know the momentum operator, that is minus I h cut del by del x. So if we calculate this parameter, this will have an absurd value in this region. So we will don't accept this type of concept, this discontinuous region we will not concept. So psi must be a continuous function and a continuous wave function. Okay, so from this figure it is clear that from this figure means this portion, I am highlighting this portion. What is the key points are getting out of this figure, that is psi equal to 0. Please concentrate on this figure. Psi equal to 0 at the time, which time? Psi or in another way I can write that psi of 0, it's a function of time, right? So psi of 0 equal to 0. Yes, this time of at the point 0 the value is 0, and at the point a and beyond that point psi equal to 0. So we can again write that psi of a equal to also 0. Right? So from this figure it is very much clear that psi at the point 0 the functional value is 0, psi at the point a the functional value is also 0. Okay, so what is the meaning of this hypothetical solution? What kind of solution is that, and how we can reach the ultimate solution? So please clear this concept before going further or expansion. Please consider this figure and please clear out this concept. Okay, now by using this concept we are again focusing that portion, that is the general solution of the second order differential equation. And what solution was there, that we have already seen, that psi of x equal to a sine kx plus b cos kx. Okay, because we are using the concept of boundary condition, so that's why we have already separated the boundary and separated the expression of that boundaries, what's the value of the psi and everything. So just we will apply this concept, nothing else. So first consider psi of 0 equal to 0. Okay, so if we put x equal to 0, so what will happen? Just it will look like that psi of 0 equal to a sine of 0 plus b cos of 0. Yes, right? So sine of 0 means 0, but cos of 0 means 1. So we are just upgraded one step to the solution of the unknown parameters, that is psi of 0 equal to 0, that is equal to b. So you are getting that b equal to 0. And we have drawn an opinion that there is no cos part or cosine solution. So there is no cos part will be there. So there will be only the sine part, right? Okay. So move to the further condition, that is psi of a equal to 0. So put the value in this expression, that is x equal to a, and what will be that? This will be because we will not consider the cosine part, because it has been already eliminated. So we will concentrate on the sine part. So what will be the value? A sine k of a, because x equal to a, that is equal to 0. Okay, so what is the solution of this integral sine and cosine term, because you have already completed this portion in your class 12 standard. Okay, so this is the solution of the integral multiple of pi, right? So nothing but the integral multiple of pi. You have already, it is already known to you. Okay, just I will use that concept. So if a sine k equal to 0, the solution will be the multiple of pi. And if we plot the region if we plot the region in between that we have considered in a boundary region, so if we plot the wave, that how the particle will move, how the wave nature in between that region, so this is 0 and a. Okay, so that is nothing but the multiple of pi, so it will be like this, pi, 2 pi, 3 pi, up to this n pi, and the number of cycles will be increasing. So first of all it will be just like this, then it will be just like this, and so on. So this is your wavical nature, and that I will draw in detail after getting the complete solution. So this is the concept of the wave in between the boundary region between 0 and a. Right? Okay, so now coming to that solution part. So Ka, if a sine Ka equal to 0, then we can write that K equal to 0 plus minus pi plus minus 2 pi plus minus 3 pi and so on. But we will not consider this, because if it is 0, K equal to 0, A equal to 0, the whole term will be 0. So there will be no solution, right? So we will we will use a general solution. What is the general solution? That is Ka equal to n pi. And we already know from the concept of the Schrodinger equation, that is K equal to root over of 2me divided by h cut. Okay, so just apply this 2me by h cut into a, that is equal to n pi. And if we solve this, we will obtain the value of the energy, because see, all are this constant. Pi constant, h cut constant, n constant, a constant, every terms are constant. So what is our measurable parameter? That is E, energy. So how can we calculate? So it's nothing but n square pi square h cut square divided by 2m into a square. If we solve this, we will get this expression. I have done in detail in your note. Please go through this line by line. So this is a quantum mechanics. Okay, so see that we are getting the discrete set of allowed energy state, because there is a n equal to 1, 2 and so on. So this is the discrete set of allowed energy, or the packet of energy. Okay, so my question is, we started with a continuous wave function, but we are getting the discrete set of solution. Okay, so that is, we can write this one. This wave function is nothing but psi n of x, because n means discrete portion. You have already studied in your signal and system that what is continuous function, what is discrete function. If it is continuous function, then it will be x of t. If it is continuous function, then it will be x of n, right? So here it is, we are getting the discrete set of allowed energy, so we will consider this psi will be psi n of x. And what is that? This is nothing but a sine Ka. Okay, a sine, just put the value of k. K is nothing but n pi by a. So a sine kx plus b cos kx, because we are not considering the cos term, so it is only a sine kx, and a sine k, the value n pi by a, we have already obtained this value, so n pi by a into x. Okay, so this is the solution of your wave equation. So this is the ultimate solution of time independent Schrodinger wave equation, right? So this one is clear. Now we have the concept of the solution we have already obtained, but now we have the if we see very carefully this term, there is until there is still some parameter that is not solved till now, that is a, because we have already solved b, we have already solved k, but this a is totally unknown to us till now. So we have to solve this a. Okay, so and after that we can say that this is the, it is not an ultimate solution. Here it is, I am wrong, it is not an ultimate solution, it is a solution of the equation, but whenever we will be able to solve this a parameter, then it will be a complete solution. And how to do that? After going back, before going to that portion, we will use some concept of normalization. Yes, because normalization concept is very important. If we can apply the probability distribution, you all know the probability, and the Gaussian curve, I think it's known to you because you have already studied the signals and systems and digital communication in this semester. So you must know that probability distribution, what is a Gaussian function. So from that concept you should know the concept of normalization. This is a very important term. And what is normalization? I am just writing the complete definition because this will help you to get understand very well. This is the summation, this is the summation of probability, this is the summation of probability of all possible points of its existence. I think this portion is very clear. This is a simple language. From where to where? Yes, from in general from minus infinity to plus infinity. And the another important point, such sum should be equal to 1, and a valid wave function should satisfy this property. Okay, if the wave function satisfies this property, then we can call it's a normalized condition. Okay, I am again just repeating this portion. This is the summation of the probability of all possible points of its existence. If we consider the region, in that region all possible points of existence should be considered, and that sum should be equal to 1. Only that case we can say that this function is normalized function. So to understand this concept, we will have the concept of the probability, and the maximum probability is 1. We all know that. And here whose probabilistic distribution will be considered? Yes, nothing but the wave function. Okay, so this wave function and the square value of the wave function should be equal to 1. And what is the expression of that? The expression will be, here I am writing this expression, that is minus infinity to plus infinity psi star into psi dx equal to 1. It is nothing but a complement value. So if we can generalize this portion, if we take the mod value, the mod value will be psi square equal to 1. Okay, so very clearly know that this portion will be equal to 1. And this is the concept of normalization, and this is the concept of probabilistic distribution. So if we know the distribution, this curve, this is a distribution curve, and here it is the region, this region, and this is the probability that the particle can move in this region. This is the region, and in very way we can say that this area under the curve, this is nothing but the probability distribution. This curve, and under this curve, what is my total area? This is the probability of that particle that can exist in that region. Okay, so this concept will be used for normalization our wave function also. And how we can solve that? Because with that concept we will denote our constant A to complete the solution. Okay, so what is the concept? Here we will begin this portion, that is we have already obtained that is psi of n equal to a sine kx. Kx means n pi by a into x. But we know that minus infinity to infinity, this probabilistic distribution value should be equal to 1. Okay, here psi means nothing but this psi n. So in our expression, this psi n will be nothing but this portion. Okay, and thus just it will be the square value. So if we take this value, and one more thing, what will be our limit, because we are considering the region in between 0 and a. So our limit will be, limit of integration will be 0 to a, not minus infinity to plus infinity. So limit will be changed 0 to a. This will be a square sine square n pi by a into x dx, that is equal to 1. Okay, so this is the total probabilistic distribution. So please see that this integration here is a sine term. Okay, and how we can simplify this term. This is my way to see that how we can simplify this integration. We all know this integration, right? But every terms have some average value. And what is the average value of the sine square term? The average value will be half. And how we can do that? Because if we extend this portion, that is sine square x equal to half minus half of cos 2x. Okay, why it is coming? Very simple, because we all know the formula of cos 2 theta. Cos 2 theta means 2 cos square theta minus 1, or 1 minus 2 sine square theta. So if we use this concept, we will easily know that sine square theta equal to half minus half of cos 2 theta. Okay, so if we segregate this term, that is half of dx minus half of cos 2 theta of dx, but here we are not considering the cos term, because in the preliminary portion we have already eliminated the cos term. So we will not consider this term. So here the average value will be half. So if we put the value is 0 to a square into half into dx, that is equal to 1, and this is a square equal to constant. Dx integration will be x 0 to a, that is equal to 1, into half, then a square into half into a equal to 1, that is a equal to root over of 2 by a. Okay, so here we have derived the one unknown term, one constant value, with the value of the solution of root 2 by a. So now our ultimate complete solution of psi n x equal to root over of 2a sine n pi by a into x. So this is your complete solution. Okay, so from this lecture we have came to know that the solution of the time independent equation, and also the discrete set of energy or the packet of energy, that is E of n equal to n square pi square h square by 2m into a square. So this is two important terms we have obtained by applying the concept of boundary condition. We have obtained the solution of the time independent equation and also the energy states of, or the packet of energy. And the last portion we have already reached, and to see that how to draw the diagram based on this, based on this solution, how we can draw this energy state and how we can calculate the wave function of related to that. Okay, so if we draw this axis just like this, this is your x-axis and this is your y-axis, right? Okay, so here this is nothing but the energy axis. This is E psi. Okay, and this is your 0 and this is your A, because we have bounded this region. Just draw the parallel line to complete this bounded region, and here we are considering some division that is nothing but the unit of energy. Suppose it is E1, E2, E3 and so on. Okay, these units of energy we can draw in this way, and this is the energy axis. So we all know the wave function is in between 0 and a, and we must have the region on this graph between 0 and a. So that's why I have bounded this region first, and now just draw that. So it's your first position, so it is a first division. So just write E1, because we all know the expression. Just before going to draw the graph, we know the expression of En and psi n. So En means n is a discrete value, n will be 1, 2, 3 and so on. So now I am applying n equal to 1. So n equal to 1 means energy state 1. This is E1. Okay, so if it is E1, just draw the line. Just draw the line and to consider that this is the wave function. Okay, so for n equal to 1, the wave function is psi 1 equal to root 2 by a sine pi into x divided by a. Okay, so pi into x divided by a means just like a pi x by a. So the solution is just like this, 180 degree. Okay, so for n equal to 2, if n equal to 2 means this is 4, 2 square, and this is again, here it is 2 pi by a. So there will be 2 cycles. If n equal to 3, there will be 3 cycles. N equal to 4, there will be 4 cycles and so on. And parallelly, for n equal to 2, this will be 4. For 3, this will be 9 and so on. So if n equal to 2, the state will be 4. That means 1, 2, 3, 4. So this is your E2. Simply draw the line and the wave will be nothing but 2 cycles, because it is 2 pi x by a. Clear? If it is 3, then it is 9. 9 means 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is your E3. And the cycles will be 3 cycles. 3 cycles means 3 half cycles. This one. And what is for n equal to 4? This will be 16. 16 means this is 9, 10, 11, 12, 13, 14, 15, 16. Yes, so this one. And there will be 4. 4 pi x means 4 half cycles. So this is your complete structure of the different kinds of energy state and the wave function, everything. Okay, so in this lecture you have came to know that what is the solution, what is the boundary condition, how to apply this boundary condition, what is the concept of normalization and everything. Hope this will be very clear to you after going through all this lecture, and please go through this and based on that try to solve the solution of the assignment. So thank you so much.